All right, so I left off with this information set, and clearly due to the writings on the board Friday afternoon, there's an appreciation for the magnesium-silica ratio, which I would remind you, in terms of building planetary bodies, really we're talking about how much olivine did the Earth accrete relative to how much pyroxene the Earth accreted. And again, I remind you, if we want to describe the planet, forget all the other elements, 4 of them, magnesium, iron, silica, and oxygen, solve the problem. If we're talking about just the silicate Earth, forget all the other elements, it's just a big oxide. Yeah, that's true. 2 of them come from his paper in EPSL in 2010, and the third one comes from his presentation at the Geoneutrino meeting in 2010. He has markedly different compositional models for his Earth in his papers.
Which is the newest one?
That may be misleading, but it's up here. But you should understand the title of the paper says an instantite or chondrite Earth model. So it should be falling between there and there. Maybe we should use the published values. These 2 are the published values. This is the one that I know he likes. It solves his problem. Right. I did this because it's important to keep in mind. I mean, Mark's model uses Monte Carlo model to calculate his composition, but this is his model. He reports in one of his tables in his paper, and this is the other one. Okay, so they're both viable models in his mind in terms. However, this is the one that fits the observational data. He has a markedly different upper and lower mantle composition, but that's what he reported, and I calculated it correctly, checked it twice. All right, so in terms of all the models, I'll just try and briefly say that there are basically 3 families of models. I'll remind you again that in terms of an element such as uranium, it's 10 parts per billion, 20 parts per billion, or 30 parts per billion in the 3 different families of models. And that just allows us to talk about the upper, lower, and the average. That difference in uranium shows up here. These elements here are referred to as the refractories. And again, I remind you, if you know the calcium content of the silicate Earth, you know how much clinopyroxene is in the Earth, you know how much calcium perovskite is in the Earth, and you also are therefore forced to know how much uranium is in the Earth. So there is no magic between what I consider the major elements and the trace elements. Aluminum is right there. Uranium's right there. I put those side by side. They're approximately similar in condensation sequence. A little difference, but the idea is that all of the chondrites have those in equal proportion. So if you know the uranium content, you know the calcium and the aluminum content. All right? The real problem is, well, this diagram, in terms of it's normalized to magnesium here and silica. Magnesium and silica are not refractory, therefore it's a model. Okay? So, how do I place the differences? Those that think of the Earth as having only 10 parts per billion uranium, or thorium uranium at 10 to the 4, sit down here. Those that think it's 20, there. Those that think it's 30, there. Okay? So, this section of the diagram is moving up or down in reference to a C1 chondrite model. Okay? Now, then there's an entire family of elements that the cosmochemical community refer to as volatile. In addition to magnesium silica, it'd be lithium, potassium, sodium, boron. But here I am only showing those that we call lithophile. Lithophile means rock affiliated. Okay? What it really means to someone like myself, these elements are found in the Earth's mantle, not in the Earth's core. I will stop briefly to say, however, some people envision that there's potassium in the Earth's core because it's needed to drive the geodynamo. That is radiogenic energy decay. David?
Silicon in the Earth's core.
Silicon could be in the Earth's core. In fact, thank you, David, for helping me to remember. I have, due to the fact that I go on forever about these things. I could not, in my own mind, justify having a subsection of slides in my talk that talks about the composition of the Earth's core and how that is determined. Can provide it offline if you need it. I would also say that I touched upon it in the CIDER 2010 lecture. So what goes into the Earth's core, the light element component, the energy budget for the Earth's core, etc., is additional information that we're really not reviewing here. So in reference state, silicon in the Earth's core, one could have some degree. See how wide that line is? That's it's an attempt to say it's a broad brush line. It's not of exceptionally small finite thicknesses, and it's sort of just a best estimate for what we believe to be the abundances of these elements under this normalization scheme in the silicate Earth. Big stop. If I've not touched the sample, if all of my colleagues have not touched the sample, if there are reservoirs deep in the Earth's mantle that have been extracted from the system, we know a lot less about the system. Okay? Any hidden reservoir means we're in trouble and we don't know how to handle it at some level.
Bill, there's a deviation that occurs sort of at high volatility cellular.
I guess fluorine would be the one that you're focused on. Yes, that's a good point to also raise. We've been talking about it with Sujoy here, and I've been talking about it with others. I remember meeting Bernie Wood in an airport, and somehow we instantly got into indium, because indium's you could call it a chalcophile acidophile element, not shown here. It too sits high. Okay, there are two uncertainties in this diagram. One uncertainty in this axis. That's where my expertise comes in. One uncertainty in this axis, and that's where someone like Dave Ruby or other petrologist expertise comes in, is what condenses out of the nebula. Okay. To the best of my knowledge, I put fluorine there, and not there. To the best of the thermodynamics community, they put fluorine there, and not there. So it's a model, and it has its weaknesses, and I can't tell you how to get fluorine to fit. And in fact, I can also tell you that all of the other halides sit down here. And in fact, when we were looking at it yesterday, we said, oh, wow, look at that. Enstatite chondrites. Remember, we like those. Have very high fluorine content. So if I divided by enstatite chondrites, that would drop right down quickly. Big uncertainties. One data point, no error bars, and, it is a great question. Next.
Would you assume that these elements condense alone, or, they could condense?
No, that thermodynamic calculation is actually based upon it condensing out in a specific phase, not as an individual element, not as in pure metal of that element. When you talk about an elements like the alkali metals, lithium, sodium, potassium, rubidium, cesium, you're really often talking about those going into a feldspar, like calcium plagioclase and sodium plagioclase. Those are the phases that are precipitating out, also sodalite. I don't want to get into all those mineral names, but yes, they're condensing out as mineral phases. And again, I remind you that this the starting point for these calculations was really by the Joint Army, Navy, Air Force division needing to know about the back ends of rockets and what will precipitate out under those high temperature condensing environments. Okay. And in deference, the Earth is a distraction down there. Sorry. Some people, when they saw this, they said, why is the Earth right there? Volatile Earth. The other thing is, this does not tell you about process. Maybe I might defer to someone like Dave for process. This is simply showing you product. Okay? So here is the product, and what I would call the integrated volatility signature for the planet Earth at 1 astronomical unit out from the sun. Right? So it doesn't mean that it inherited these elements and these abundances from day one. It may be that day one, the volatility curve went like this, and at day 15 into the accretion, it had much more of a component up here. So I don't know how it got to this state. I have simply, as best as I could, described its final result. Okay? So that's another thing to keep in mind when looking at diagrams like that. Yes and no. The question was, are the uncertainties of this diagram represented by the size of the data point? And some of them, yes. A lot of these up here, yes, by the size of the data point. But, for instance, I would say I'm very satisfied that the uncertainty on potassium is based upon the potassium-uranium ratio of approximately 14,000 with a 2 sigma uncertainty of around 3,000. And I can't remember the exact number. It might be 3,300. So, in fact, I would have an error bar on potassium at some level. I don't put all the error bars for all the elements on there.
This is all samples all over the Earth?
All right, question from Barbara was, this is all samples from all over the Earth. This is the end result of looking at samples from around the Earth. Some of them represent samples of the continental crust. Some of them represent samples of basalts. Some of them represent samples of komatiites, the early Earth high-temperature magma series. And then some of them represent samples of the mantle, peridotites. You really need to integrate all of that information. It's no different than integrating all of the waveforms in seismology.
If you use, say, an institute model, does the volatility trend just translate in space, or does the slope actually change?
Okay, good, really, really good question. If I use an anstatite chondrite model, how does the pattern change? Okay, if I was to plot up here a C1 chondrite, it's flat at 1. Okay, and I will show you that in a couple of slides. All right, if I don't, well, I think I'll remember. I'll show you exactly how that changed. That's a good question. Yes, it's an important question because the question really was asked, are you using the right reference frame? Who knows? It's really important. To all of us in this room, the amount of potassium, thorium, uranium in the Earth is of considerable interest, and it goes right across the disciplinary boundaries, because if I, as a geochemist, say this is how much thorium, uranium, potassium is in the silicate Earth, if not the bulk Earth, the petrologist can work with that to see why it ended up partitioning in that way. The geodynamicist can see how much energy is available to run the Earth's engine. Okay? So that's important. Additionally, it's important to look at some of these other bodies. Here's an array of data for the Moon with, on average, the potassium-thorium ratio is 360. A guiding principle in our business is that the thorium-uranium ratio in chondrites is 4. Now, I said the number 4 because it gave you just one significant figure. Catch me on another day, I might say 3.9. Catch me on another day, I might talk about the range of values measured that goes approximately 3.5 to 4.1. We're not talking about values of 10, 20, or 1. We really are talking about values of 4, and if I want, I could say 3.7 plus or minus 4, or something like that. Cover really the range of data seen there. So when we talk about potassium, thorium, uranium, we'll often talk about thorium-uranium ratio of 4, and a potassium-uranium ratio of some number for the Earth around 10,000. But a lot of people tend to know this number, Ku ratio. The Earth, my best estimate is around 14,000. Mercury is now being estimated at 20,000. Mars, now there's a head scratcher. Mars and Mercury, close in and on the other side of the Earth, having the same Ku ratio. The implication is, particularly from the last diagram, they have the similar volatility signature. Some people don't like that. Some people like that. Okay? The Moon.
How is that determined for that degree?
Oh, I'll get to that in a couple more sentences. The Moon here, well, if you look at the Moon, it has a really low Ku ratio. Frankly speaking, if we sort of set the thorium or uranium abundance based upon the refractory inheritance that these planets got, the K is telling us about the volatility budget, and it's not easy to dial up a scenario where the inner and outer terrestrial planets get a lot more volatiles and the Earth gets a lot less volatiles. I'd like a little systematic in this system, but it's not showing up. All right, now let me address Dave Ruby's question, which is quite valid. How do you get these ratios? First off, we have Martian meteorites and we have lunar meteorites, but we don't have any other meteorites from Venus or Mercury. Okay, that's one important thing. So when we have meteorites, we can take it into our labs and measure it. But there's, you can go and get a rock from the surface outside. You can get carbonates, sandstones, everything walking around the street here. You can get a range of Ku ratios and you go, well, what's the whole Earth Ku ratio? Okay, so that's complicated if you have any one sample. The other thing that's frequently done is they have gamma ray surveys around bodies without atmospheres. Why is that? Because of the gamma rays emitted during the decay, you can actually measure them, but they will not go very far because they'll interact with the atmosphere and the energy absorbed in the system. So when you're talking about satellites going around the orbiting the moon, you can actually do a beautiful gamma ray survey of the surface. Similarly, for Mercury, they're doing both gamma ray surveys and they're doing X-ray surveys. You can actually get potassium X-rays. So the most recent measurements for Mercury, and this was a science paper on the recent Messenger mission results, are giving you some sort of impression that Mercury and Mars's gamma ray survey also, have similar thorium-potassium ratios. I'll show you a difference here. This is what they report in the paper in Science. I made this table up. They say 5,500. And where did I go? I said 5,000. The reason I said 5,000 because they reported the potassium content plus its uncertainty and the thorium content and its uncertainty. And the values actually range between 3,000 and 8,000, almost 9,000. So let's not get carried away with sig figs here. It's about 5,000. Okay, so that's the kind of number. But is that going to be the entire planet? We do not know right now. Okay, it's a complex body, and these are the first data out. But the bottom line from this diagram is that there's a range of Ku ratios in these planetary bodies. And for me, it's enigmatic because I don't know why the Earth ended up being the more volatile, depleted of the terrestrial planets.
Should we also be interested in the absolute values of these numbers? Mercury, for example, has very low concentration.
Okay, if you didn't hear that, absolute concentration versus relative concentration. And just turns out, it's regrettable, but we can do ratios far better than we can do absolute numbers. And yes, we should, because then the absolute concentration, such as in the Earth, is at 10, 20, or 30 parts per billion uranium. The absolute concentration really tells you about the power budget for radioactive elements. So no question about it. We want that number, but it's darn difficult. I love the Messenger mission, but I would rain on just about every chemical story I've heard from the Messenger mission because one has to be very sensitive to the fact that we're just getting, tens to hundreds of micron depth information from most of these chemical signatures. So every time I hear that the Messenger mission tells us that Mercury is a volatile-rich planet because it's got lots of sulfur, I just said, no, this is a planet that has lots of sulfur, at least on the top few microns. I do not know how much sulfur is inside that body. Mine is an N-member position. I'll just highlight as you look at this, Curtis, this is the exact question. This can address that question. And particularly, I didn't do it. Forgive me for putting in all the horrible details. Green is anstatite. This sort of golden type color is ordinary. And these blues are carbonaceous chondrite. Ed?
I was just curious. In the last plot, there's a line that goes through a big cloud of data. What does each point represent? Like our rocks, is that variability?
Good question, Ed. I cannot answer that. I think for the moon it is, but it can't be the case for Mars. It cannot be the case for Mars. We don't have that many. So it must be small footprint integration gamma signals. You know what I mean? As the satellite's going. I can answer that offline, but I have the paper in the computer. No, the blue one was the moon, and the gray one was Mars. Okay, we'll go back. That's Mars. I know. I'm standing in front of you and saying, I know that. But see that gray that says 5,500? That's not the Earth's. The Earth's, this is Mars. I can tell you right here, this point is from the Venera mission. And I forget these light ones. These are the moon. Oh, I think those are Martian meteorites, the light gray ones. See these light gray? But this is an array from Mars. And by the way, if you wanted to see, quote, rocks for the Earth, it would cover this page. Okay? That I can give you with a high degree of confidence because granulite facies rocks from the lower crust, really have the greatest amount of variation in Ku ratio because potassium is a mobile element. It goes all over the place.
So is that really a Venner measurement?
The orange one right there would be one of the Venner emissions. I covered most of the Venner up because I don't want to talk about it because you don't know much about what Venner is telling us. Someone was saying something here.
I'm just trying to say the same thing. That's supposedly Venus.
Yeah, Venner is the Venus mission by the Russians, and that's, you know, it's enigmatic data is the best I can say.
Do you have any other meteorite that would fall on the line Mars Mercury?
Do I have any other meteorite? What?
That would fall on the line Mars Mercury.
Marked Mercury. That sounds like a leading question. Are there any meteorites that fall on the line marked Mercury? So what if we do? I would not go on to say that that's a Mercurian meteorite. So I wanted to address that question as potentially misleading because, and I'm not opposed to the idea of a meteorite being from Mercury, it's just that I can find rocks from the Earth that sit on that line. And wouldn't surprise me in the least I could find a meteorite that falls on that line. This one, yeah, these. Gamma ray survey stuff, yeah. And so that's why I was paused for a second, because I'm going, yeah, I know how to integrate the entire global surface, but they must have partitioned the gamma ray survey for Mars into smaller footprints, and that's why there's so many data points for Mars. So it just struck me as unusual. Yeah, believe me, I could fill up this diagram with terrestrial sample values. There's two aspects to this diagram, and I don't want to spend too much time. It's really a summary diagram, but the refractories are here, and there's lots of them. We can use them for lots of chemical stories, and the volatiles are there. First thing to take from this diagram, the green lines go along here. There's magnesium, there's silica. It goes up a little bit for silica, for magnesium, up even higher for silica, and then the volatiles are over there. So from your position, you can see that these elements are actually slightly lower than those volatiles, but about the same as those volatiles. How do I interpret that? There is no volatile depletion in the ansatite chondrites. That's a simple takeaway message. Ordinary chondrites, this golden line, flat, 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 down a little bit. But a little bit is not much. And then the blues up here are above the line 1. Remember, 1 is C1 chondrite. And then the blues go down below the line 1. And then the earth, which is this red dotted one, goes way down. So even in terms of volatile depletion, the earth stands out from the chondrites. And the chondrites, remind you, undifferentiated. They're an intimate mixture of metal and silicate. Okay? Now, if we look in this diagram up above, it's two element ratios. Rubidium to strontium, potassium to uranium. The element in the top, rubidium and potassium, are volatile. The element in the bottom, strontium and uranium, are refractory. The sun, which looks like C1 chondrite, sits there, so that's your reference frame for this diagram. The ansatite chondrites are up there, the carbonaceous chondrite down there, and the earth, my gosh, in this diagram, the earth is strongly depleted in volatiles. Okay. So chondrites are a guide, not at least if I'm right, or if a number of us are right. You know, there's a massive depletion in volatiles. Go ahead.
Why is the moon Mars Mercury on this diagram?
Because I didn't want to clutter it up, but the moon rocks are down there. We just do not find moon rocks. I mean, every time we look at the strontium-strontium isotope ratio in moon rocks, they're really low, and it just tells us, hey, there isn't any rubidium around. And the same for the potassium-uranium ratio. And if we added Mars and Mercury, not enough data in that system. I'm just going to skip that. Believe me, I've got to give it to Sujoy. Rick Carlson, I believe, introduced oxygen and showed something like this diagram. Kevin McKeegan really showed that this is actually the measurement, the solar wind fractionation. This is our best estimate for the sun. This is where we have most of our discussion in this blue box. That's where most of the discussion is. So when we even talk about the sun's oxygen isotopic composition, we're way far away. You know, remember how far away we were from the sun? And then we're actually splitting hairs about, here's LL, L, and H chondrites. These are the ordinary chondrites. These represent 80% of all the falls that have fallen. Okay, they're not too far from this fancy line that we like to, well, we must be on, that dashed line. We must sit somewhere on that dashed line. The moon sits somewhere on that dashed line, too. I think it's that red dot. Mars is just above it. We don't know where Venus or Mercury sits on this line. Okay. So there is a bunch of the carbonaceous chondrites, and on this line is the Enster-type chondrites, and that's why we really like the Enster-type chondrite model. But it makes us scratch our head, and we don't know how to interpret it, and we have to remind ourselves that the sun, the solar photosphere, the solar wind, is very far away. All right. Next most enigmatic situation. What you'll hear from me will deviate markedly from what you hear from Rick Carlson. So this is an area where there is discussion in the community. Okay. First point I want you to take away from there. Are there 3 different colors of chondrites? Yes or no? Work with me, folks. Forget the white dots. That's special pleading by special scientists. Are there 3 colors? Yes or no? It doesn't matter. Yeah. Okay. Just do you see the colors red for some that are squares, yellow for some that are diamonds, and blue for some that are circles?
Is this a color
All right, so is there solar system heterogeneity? Chondrites a guide or a requirement? These are 3 questions I want you to keep in mind. Do planets equal chondrites? Same diagram. And I never told you that this sort of blue shaded region is the terrestrial sample. Rick Carlson showed us the most recent compilation by Matt Jackson, who'll give a talk later today, and Rick Carlson. And this is a very fair representation. But I will tell you that a lot of people have emphasized that the value for chondrites is this yellow thing. And I thought there was a great paper out by the team at Carnegie Institute, Chin, Cornell Alexander, and Rick Carlson, where they actually took, I believe, an ordinary chondrite and a carbonaceous chondrite, nearly dissolved it, but did it incrementally, and found components, like Rick told us, that represented, let's call it, different proportions or contributions from what we would call the R process and S process of element manufacturing from supernova environment. Okay? And in fact, in that paper, they showed that there was a residual sample, I believe it was, could have been the leachate, that really plotted way down there, and it represented an R process excess material. And then there was another fragment from this leaching process that plotted way up there. That was an S process product. And really that was, for me, another major evolution in my thought and revelation. I had been fighting for a while that people kept arguing that there's a difference between this, and that difference needs to be explained. Okay? And then this paper came out. And then actually a few weeks ago at Goldschmidt, the exact same experiment was done in terms of looking at potential R and S process components in Enster-type chondrites. Here's my conclusions. First off, the blue box is not, oh my heavens, how'd that jump ahead? The blue box is really much more representative of the modern terrestrial Earth based upon the data that's out there. Secondly, I ask and I beg, please stop saying that the epsilon 142 is, for the Earth, is 18 ppm higher than chondrites. There's your 18 ppm. And the basic point on this diagram is really, do you see black, red, green, and orange or golden color? There's a variation that we're measuring in the solar system. And in fact, I actually now see the 142 system as a fantastic measure of the efficiency of homogenization of the solar system. Okay, so we're now recording with these isotope systems that we've only been able to achieve measurement of in the last decade. Down here, we're really talking about parts per million precision in these measurements, and differences might actually represent how well the system was homogenized. Okay? So, the model for 142 neodymium basically says, I think there are two solutions. One, there is no problem. That would be my perspective. The 142 data record an efficiency of mixing in the nebula. The alternative assumes that the mantle has a specific 142 chondritic composition. By the mantle, I really mean bulk silicate earth. But I needed to find my words correctly because there's two solutions for this model. Store it deep or lose it. The traditional model that came out in Rick Carlson's EPSL paper, which believe me is fundamental and one of the really most exciting results in the last decade for me, is there's an early Earth enriched reservoir deep in the mantle, at the core mantle boundary, if you will. Why do we appeal to a hidden thing? Because if in the previous diagram there is an 18 ppm difference, his model is great because it helps us to solve that. My model says there isn't. Now there's an alternative model that says that the way Boyett and Carlson came to their model was they differentiated a crust, stored it, had a light rare earth enriched crust, and then sunk that through processes, brought it down to the bottom of the mantle, and kept it there forever. O'Neill and Palme said that crust was available for being hit by a home run, you know, by Mickey Mantle, the guy that used to actually take the crust off of the Earth. No, nobody got that one. The enriched reservoir was lost to space through a collisional process. Okay, so you either store it or lose it, one or the other. But that will solve it. There's a complementary reservoir. Okay, so.
There's another explanation that there's 6 or 7% variations in neodymium through the structural plan.
Yeah, you're right. That one it's less desired, but I couldn't actually, in the end, see that being different than the O'Neill and Palme result, because they say that the Earth has a fractionated samarium neodymium ratio. You could also have you get the same result from their Earth model.
Well, I'm not advocating this all as a model, but in fact what it's saying is that there is no early enriched reservoir.
Right. So that is the fourth issue, and this is one we definitely stay away from because it means that on a rare earth diagram, samarium and neodymium are next to one another. There's actually a missing element that's not stable, only in stars. When it's chondritic, it's flat. When it's the continental crust, on the normalized diagram, there's a bit more neodymium. When it's the depleted mantle, there's a bit less neodymium. And we're saying maybe the bulk Earth had this kind of composition. The bulk Earth had this kind of composition. And that's always been unsatisfying, even from the day it was proposed in the Boyett and Carlson paper, because it's outside the spread of chondritic meteorites. It sort of sticks its tongue out, if you will, at the idea that the Earth is, the refractory elements are in chondritic proportions. This is really way outside that ratio. So that's why it's always, Mark's right, but it's always not favored. It's hard to live with. The other penalties are really nasty.
Is that line different from the efficiency mixing?
Line 1, the model 1, no problem. I think it's the 142 story is just telling us about efficiencies of mixing.
Is that different from what Mark just mentioned?
Yeah, but that would be that'd be a really bad, yeah.
The Trump was proposing to not produce rare earth gas in the Earth. It would be nice to have some physical mechanism that you can separate these elements. For things like the volatile elements and the sideral elements, you do have physical mechanisms. But separating refractory elements from
Right. This is a big issue. And for me, it's a very big issue because I've always played by the game that the periodic table is not a one-stop shopping place. So if we've done it for samarium relative to neodymium, we've done it for lanthanum relative to neodymium, we've done it for cerium relative, we've possibly done it for calcium relative. It's just, oh my God, there's so many penalties you pay for that kind of, let's get outside the chondritic refractory ratio box. It really, and there's just basically no observational information that provides us that permission to go way outside the refractory ratio box. It's really.
I'm not advocating.
No, but you're a healthy addition of information.
For full disclosure.
Full disclosure.
The serious scientists proposed this.
Right. Right.
We didn't have a mechanism for tight tectonics, so
Right.
saying there died on a glacier, a broken man, doesn't mean that there isn't tight tectonics.
Good, Mark. Paul Warren made this observation in EPSL in November. Remember, I had 5 statements that said, the Earth is this, the Earth isn't this, the Earth is this, the Earth isn't this. This was the last one, and I know that Rick Carlson showed it. And the Earth ends to tight chondrite. There's similarities. There's no question about it. We don't look like carbonaceous there. We don't look like carbonaceous there. We don't look like carbonaceous there. Guess what? The Earth constantly plots really close to ends to tight chondrite. The Earth plots close to ends to tight chondrite. The Earth plots close to ends to tight chondrite. Pay attention to it. That's the bottom line. But what does it mean? This is my Earth. Okay? So my Earth is like an ends to tight chondrite, but the MGSI ratio is very different. Or at least very different amongst what we know today about ends to tight chondrites. The other way to understand this, the ratio of olivine to pyroxene. Okay? There are shared isotopic compositions. This is the growing family. Let me remind you, there are also some isotope systems, such as silicon, Fit2C and bourdon, that says, no, the isotopic composition is very different from ends to tight chondrites. So for every 4 isotope ratios that look like ends to tight chondrite, there will be another one that says it doesn't look like ends to tight chondrite. I'm going to emphasize that word like. Okay? Shared origins unlikely. I was asked, what do I mean by that? This is a chondrite. And I actually like when Rick Carlson was saying we're accreting pre-differentiated bodies. And chondrites actually happen the day after the solar system born. But we have these products that are tens to hundreds of millions years later. There's a big jump between those two products. Keep it in mind. That's why I say shared origins unlikely. Be careful what you mean. Core composition, well, if you're going to go to ends to tight chondrites, people have done that and stuck potassium in the core. But you would also stick uranium and thorium in the core because an abundant sulfide is oldemite, and it's got hundreds of parts per million thorium in it. So, woo! So I want to say like an ends to tight, but I don't want to pay that penalty. I'm not in the mood for paying that penalty. Okay. Chondritic Earth concept, useful concept, but it's not a requirement. It's not like a parking ticket. You have to pay it. You do. So Javois model, I think pay attention to it, but it needs gross modification. Last couple of things.
You could also add oxygen fugacity to that list.
Right. He said you could also add oxygen fugacity, which is to say, I am going to stay right with the composition of ends to tight chondrite. Well, the ends to tight chondrite, you have to remember back 25 slides earlier in my other talk, I showed about the redox state of the various things. In the redox state of ends to tight chondrite, silica goes into the metal. Okay? The redox state's really important, but we cannot. One of the things that's really impressive, why did isotope stories marry up with redox stories? We don't know that yet. One sinful statement I hear all the time is the ends to tight chondrites formed in the inner portion of the solar nebula. And that means that scientist already knows the time and place of formation, or time or place of formation. Okay? I don't know how they know it, and I'm really not a big enthusiast of really assigning position in the nebular environment for formation of chondrite families.
In your previous slide, number 1, Jackie mentioned Pero-Murakami recently. What's the implication of that to your statement number 1 and 2?
That there is much more silicon in the lower mantle than in the upper mantle.
Was that helpful for him?
Yes. That you remember we were talking for a little while about Marc Javois, the first figure, and the 3 stars for Marc Javois. The position of those stars. Oh, let me just go to there. I'll show you because it's really important. This means that the compositional distinction between the upper mantle and the lower mantle starts at 670. This is a little deeper, and there's only a small amount that's very deep. Okay? So really, you're going from here to here to here represents how much of the lower mantle is olivine poor.
Bill, to be more specific, if Murakami is right and the lower mantle is a perovskite,
Mm-hmm.
and that's 3/4 of the mantle and 1/4 of the mantle, where are we?
Oh, no. I think Murakami really is not so specific to say below 670 is perovskite.
Pretty close to that.
He does really say below 670? Wow. I mean, go, whew. Yeah? All right. Yes, but I would have said maybe he'll start at 1,000 kilometers depth or 12.
If the lower mantle is a perovskite.
Isn't or is?
Where does the bulk earth plot, or excuse me, bulk silicate earth plot on that diagram?
Where does Murakami says CI chondrite, but the reality is it's somewhere below that. I know that. See, if I remember right, I could.
The lower mantle is a perovskite, so 3/4 of the mantle.
Oh, if it's pure perovskite, that is no magnesiowurstite?
And 1/4
Down here.
of the upper mantle. Okay, so that's the extreme model
Yeah.
for the Earth based
Yeah.
on possible Earth observations.
To my if I need to be corrected, I'm going to check it right after this. But yeah, it's down there. It's down there. And in fact, I remember about a month before coming here, I was writing to Abby Kavner, and I says, Abby, I really want to get that number really hard. And she goes, no, it's really how you partition all these elements. And Abby used to be here, and she'd give some of the mineral physics for calculating the bulk composition, and basically told me I can get into some arguments with people if I was to assign the formulas for the composition of magnesium-perovskite deeper in the earth. That's why I wanted to give you that exact number, but Abby said, be careful. But that's important. That's really been where that debate is going for a long time. Oh. I'm supposed to transition. I have 3 slides left. Okay. So basically, I end up saying this. This is when I was supposed to transition, right at 9:30. So this said there's 13 nanograms of uranium in the earth. There's nothing in the core. Everything's in the mantle. This is where petrologists, geochemists sit. Okay, Palmy and O'Neill or Marc Javois sit here, half of that. Turcotte and Schubert, a bit more. That's one of these geodynamic parameterized convection models. Okay, now, however, the Earth is differentiated. Really, in my model, half of the uranium is in the continents and half of it's left in the mantle. That kind of number. Okay. Oh, I'm just going to tell you this, and you can ask me later. The late veneer is not to be confused, or the late accretion is not to be confused with late heavy bombardment. But when we're going to talk about the first billion, whatever billion is, Mark and Sujoy's later arguments, I'm going to tell you that there's some really exciting, fun things happening in the geochemical literature. The highly siderophile elements in the Earth's mantle, to the best of our knowledge, there are some others, but to the best of our knowledge, we think they all came in afterwards because their partition coefficients doesn't make sense for them exchanging between the core and the mantle. Okay, so how did they come in all on Thursday? A billion years after? Or did they come in every other week, a certain increment? Well, in 2009, Meyer et al. In Nature said from 3.6 billion years ago to 2.6 billion years ago, the absolute concentration of the PGEs has been increasing in commodithites. And then here is the platinum, and here is ruthenium. Increase, 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 and then ever after, they're all there. And in the same line of reasoning, a great paper by Brian Connolly and Igor Puchtel and many others get this fabulous isochron from these komatiites from southern Africa. And basically, this is his diagram, and he's showing that the earliest komatiites, almost 4 billion years old, have very low PGEs. This is the present-day Earth mantle, and there's a secular evolution in the abundances of PGEs in the source regions of komatiites. Now, I don't have it, but the Tabul article that come out looking at komatiites. Komatiites are really Mg-rich magmas, probably due to high-temperature magmatism early on. Let's see. Oh, I can't remember right at the moment, but basically they found heterogeneities in tungsten that shouldn't be there. So what did they say? The mantle was not efficiently mixed after core formation. So 2.7 billion year old komatiites have tungsten isotopic heterogeneities that are preserved from core differentiation phase. That's the best way to interpret that data. So in the last decade, we've really improved our technologies, found some new things where we weren't expecting. And I'll tell you right now, there are some people in this room probably saying, nah, we were not accreting late veneer during the period 2.6 to 3.6. But the data seem to support it right now. So that's really for the dynamicists, for growing the Earth. The late veneer represents less than 1%. But, you know, it's almost a moon-sized contribution to the Earth.
Well, I tried to show that you get a similar story in 142 Neodymium variation in the early Earth, where you see this level of variation in the...
Yes, I remember the new...
You don't see it in younger stuff. And neodymium is not sensitive to late veneer at all, simply because of the mass balance of refractive profile. It's not affected by late veneer. So what the interpretation here would be is that this is mantle mixing and not necessarily a late veneer.
But I'm trying to present their models, not... Their models are saying it's late veneer additions.
My recollection is that they're saying that the mantle was poorly mixed.
There are two families of interpretations in there.
The paper itself definitely says that that's the time scale for mixing the late veneer into the mantle.
And that doesn't, remember, he said it, and you can interpret that as...
I read it last night.
Okay, addition or not addition. And in fact, I have presented a model that said, using some observations that were talked about by Scott King and Louise Kellogg and others, that you can still have what's called an endogenous model. You could actually sweep up off of the core mantle boundary surface some amount of the core. It's extremely inefficient. And that's when it really crystallized in my brain. That inefficiency is equal to the amount of highly siderophile elements in the mantle. So in fact, it has nothing to do with it incoming. It's incoming from below. Mathematically, it works.
Do you think you have any chance of sampling a high platinum, high ruthenium, early reservoir height to complement to the mixing here?
You know, when you started that sentence, I said, do you think you have any chance of finishing this section of the talk, Bill? That's a good question. Please forgive me. I'm not going to answer it. I've got to let him talk. Oh, final thought. It really was talking about the amount of heat. Remember I said 10, 20, or 30 parts per billion? This is a whole story about the power of the Earth. This is today. And today, you know, we think, well, first off, put your hand on the blue sphere and you get about 46 terawatts of power. We think about half of that, 20 terawatts of power, come from radioactivity. However, this diagram scales down if you're Javois and O'Neill, scales up if you're Turcotte and Schubert. Okay? But, you know, to put it really in perspective, this is a simple calculation. This is what happened 4.5 billion years ago. We had over 100 terawatts of power. Boom. Factor of 4 more than today. Right. 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 I'll put it in perspective. Today, I think we started with 40 parts per billion, and we're left over with 20 parts per billion because we've gone through one half-life of 238 uranium. All right, so this pi diagram, the second last slide, is Homer thinking about pi. The Earth's core, we don't know that so well, but it could be some number like that. The Earth's mantle is really the leftover after 1. If you like my model, it's the continental crust is around 8 terawatts of power, and the mantle has 12 terawatts of power. If you like Marc Javois' model, the continental crust has about 8 terawatts of power, and the mantle has 2 terawatts of power. If you like Turcotte and Schubert, 8, and the Earth has about 23 terawatts of power. Okay? So really, what is the radioactive power in this block of material? That's the way to think of that. And that's the way to think of all of our different chemical stories. I'll skip to neutrinos, and then I'll leave it right there. You can read it. We can talk about it, but you're up. Sorry. There's so, I think everybody wants to become a geochemist because there's so much exciting, fun stuff. Oh, let me add an advertisement moment. Matt Jackson's actually going to be talking about some of this cool stuff in this afternoon's seminar. Right, Matt? Yeah. The fun has not ended.
So I told Bill last night that it's going to take him an hour to go through, even though he was really adamant that it would take 45 minutes. So I'm going to talk today primarily about noble gases, and then in the next geochemistry lecture, couple the noble gases to the other volatile elements, carbon, hydrogen, and nitrogen, while talking about the early atmosphere. So if you notice, Bill's Earth did not have any noble gases in them. And maybe one of the reasons is because it's really out to the far right of the periodic table. And Bill doesn't like dealing with right-wing nuts. But if you look at the published literature, there's a lot of measurements of helium isotopes. And there's a lot of interpretations of how the mantle works based on helium isotopes. There are much fewer measurements of the rest of these elements down here. And this is something I'm going to take from Bill, which is if you build a story based on helium, it has to be consistent with the story on neon, argon, krypton, xenon, and so on. We don't think radon is particularly useful because it has too short a half-life, about 3.5 days. So just a couple of quick definitions. Often we use terms like primordial noble gases to refer to some of the isotopes like helium-3 or neon-22 or argon-36. And when we talk about primordial isotopes, what we are implying are basically isotopes that are not produced on the Earth by any kind of radioactive decay or any kind of nuclear processes. On the other hand, we'll talk about radiogenic noble gases, and those are isotopes like helium-4, argon-40, or xenon-136 that are produced through radioactive decay, or for neon-21, they are produced through nuclear reactions. And typically, we report the isotope ratios in terms of radiogenic to primordial, with the exception being helium, because we report it as helium-3 to helium-4. But I think it's high time that we correct it, although I think in the geophysical community, people are used to 3-4 ratios much more than 4-3 ratios.
Don't you make helium-3 from tritium decay?
Tritium made from nuclear reaction? Yeah, but not in the Earth's mantle. In the Earth's mantle, you could potentially make helium-3 from a lithium N-alpha reaction, but there isn't a lot of lithium in the mantle as well. Okay, so when you look at the elements, there's a whole zoo of isotopes. And one of the beauty with the noble gases is that they're inert, and there are some chemical coherency with how they behave. So in blue boxes are the isotopes that we think are produced either through radioactive decay or through nuclear reactions. So, for example, helium-4 is produced from decay of uranium and thorium. Neon-21 is one of those isotopes produced by nuclear reaction involving O18 alpha N, meaning you have an alpha reacting with the O18, spits out a neutron, you produce neon-21. This is an N-alpha reaction on magnesium-24, which produces neon. One of the beauty of the system is that the alphas and the N's are basically sourced from uranium and thorium, which means that there is a proportion of helium-4 to neon-21 production in the Earth's mantle. So you can look at rocks and figure out things like, are the helium to neon ratios in the rock fractionated from what's in the mantle? Because in the mantle, these two are going to be in the production ratio determined by the uranium-thorium contents. When you look at argon, these two are the primordial isotopes, 36 and 38, and argon-40 comes from the decay of potassium-40. And here is the link to the potassium content of the Earth, because if a certain amount of potassium is present in the Earth, then a certain amount of argon-40 will be produced. We know how much argon-40 is in the atmosphere, and so given a potassium content, we can figure out how much argon-40 is in the mantle. And in the geochemical tutorial, we're actually going to look at this in some more detail. But argon-40, just for historical purposes, argon-40 is one of the isotopes that has been used to argue for a relatively large undegassed reservoir, because based on, say, potassium contents of about 280 parts per million, the atmosphere and what is present in the MORP source does not balance the budget of argon-40. And that's another reason also why people have looked and investigated if the potassium content of the mantle is indeed 280 ppm, or could it be as low as something like 150 ppm, in which case there is no problem in terms of balancing the budgets. Krypton isotopes, I'm going to skip over for this lecture. I'll touch upon this in the next one, partly because there is some amount of these isotopes produced from fission of uranium, but the measurement precisions are not really high enough in most samples to detect them. And the final one is xenon, which is about 9 isotopes, a whole suite of isotopes that are primordial, and then a whole suite of isotopes that are produced from radioactive decay. This one is important, xenon-129. It is produced from iodine-129. Iodine-129 has a very short half-life, about 15.7 million years, which means that the production of this isotope is over roughly after 100 million years. So the system is dead after 100 million years. These isotopes, 131, 132, 134, 136, are produced from spontaneous fission of plutonium-244, which is another short-lived isotope, half-life of 80 million years, extinct after about 500 million years. And there's some amount of these isotopes produced from uranium fission, and that's still happening today. So some of the things that we have to worry about while looking at noble gases are things like solubility, which does not affect things like samarium, neodymium, and so on. So in terms of their relative behavior in the melt, helium is going to be more soluble than neon, which is more soluble than argon, which is more soluble than krypton, more soluble than xenon. So basically, the melt prefers helium much more than it does xenon. The solubility ratios are for helium to neon are approximately 2, which means that if you have a closed system degassing, the melt will increase in its helium-neon ratio by something like a factor of 2. The helium-argon solubility ratio is 10, and again, that means if you have closed system degassing, this ratio will increase in the melt by about a factor of 10.
Is this scaling with size of the atoms?
Yes. In terms of the behavior during melting, this is much more controversial. These are really difficult experiments to do, and I think only maybe in the past 6-7 years are we starting to get data that we think are reliable. We know that these noble gases are incompatible, meaning that they very strongly prefer the melt over the solid. The helium partition coefficients are low, somewhere in the range of 10 to the minus 3 to 10 to the minus 4. Likewise, the neon partition coefficients are also very low, on order 10 to the minus 4, but this is basically just based on this one study by Heber et al. I think we certainly need a lot more data for figuring out the precise partitioning coefficient, but I think it's fairly safe to say that these are highly incompatible elements. And so the take-home message would be that if for partition coefficients down here, melting is not a very good way of fractionating, say, helium from neon, meaning that the melt and the original mantle will effectively have the same helium-neon ratio, because the melting process effectively transfers all of the helium and neon into the melt, and as a result, you don't fractionate them. And I'm going to just illustrate this in one very simple way. So let's assume you have a mantle that's convecting. You melt a part of the mantle. You produce your melt and your barren residue, because most of the helium and the neon have gone into the melt. So you could think of this as the plate, the oceanic crust and the depleted Harsberg residue. And then you take this plate and you subduct it back into the mantle. And if you have degassed the melt upon eruption, then what you're subducting back effectively has no helium or neon. So the end result is you end up diluting the concentration of this reservoir, and you can show that given these very low partitioning coefficients, as a function of the mantle overturns, the helium-neon ratio effectively stays constant. If you think that there is actually recycling associated with these plates, we're pretty sure that helium is not being recycled based on measurements of exhumed peridotite or eclogites, but it may be possible to recycle neon, in which case this helium to neon ratio is going to actually start decreasing in the mantle as a function of overturn rate. So either the helium-neon ratio in the mantle does not increase significantly or it decreases in the mantle. It's very hard to increase helium-neon ratio through any kind of plate tectonic processes that are operating today. So when we are trying to figure out if there are different reservoirs in the Earth and what might have happened in the early Earth, we rely on places like Hawaii or the bottom of the oceans along mid-ocean ridges, where you see some very nice, beautiful pillow lavas. You also see very beautiful fresh lavas out here. And this is one of the reasons why I'm really envious of people that can make super high precision tungsten or neodymium isotope measurements. Even though these lavas are really fresh, they're absolutely horrendous for making the noble gas measurements. If you're not a geochemist, could you explain why? Any ideas? They degas, exactly. These lavas are erupting under water depths of 3-4 kilometers, and that prevents significant degassing. These lavas are erupted subaerially. They are completely overprinted by the atmospheric noble gases. I'll give you some estimates tomorrow, but basically we think about 95 to 99% of the noble gases are actually in the atmosphere, not in the mantle. So it's very easy to overprint the mantle signature for these plume-derived lavas. So we have had relatively good data for mid-ocean ridges. It's been much harder to get a data for plume-derived lavas. So people have sampled through submersible basalts of Luihi that go down to water depths of 2 kilometers. And even in those samples, it looks like a lot of the basalts have been overprinted by atmospheric contamination. So for example, when we measure the neon isotopes, they look pretty much like air. But there are some anomalies, and that was actually one of the first areas that was shown to have non-atmospheric neon isotopes by work by Honda and his colleagues in the early 1990s. But when you look at argon and xenon, those measurements are, we think at this point, being overprinted by atmospheric contamination, Ed.
Does degassing happen at the vent or all the way out? Like if you were to sample this, like if you can magically go in with depth?
It probably happens all the way from the magma chambers till eruption. Or in the deep earth.
You can't hope to drill down into these things to be below the degassing.
There is no guarantee. We do find some samples which look like they're undegassed because they have the helium-4 to neon-21 in the same proportion as you would predict based on its production ratio in the mantle. Or it has the same proportion of helium-4 to argon-40 that you would predict based on the potassium to uranium ratio in the mantle. So
you don't get to enjoy a gradient that you see that stops.
No. No. If there was an easy way of actually looking at a sample and saying, aha, that's an undegassed sample, that would be great. But there isn't, unfortunately.
Doesn't this degassing on the left give you an opportunity to collect the volcanic gases that fumarole? If you're worried about fumarole gases, you've got an integrated technique for
So that's a good point. Although based on all the studies that have been done, especially for Hawaii, when you collect the fumarole gases, they look very much like atmosphere, meaning that somehow air is being introduced deep into the system. So for Kilauea, we think at least that there's a shallow magma chamber, maybe about a kilometer or so below the summit crater, and it looks like there is somehow air getting into that magma chamber. So this is not an easy problem to do, and that's one of the reasons why this area of geochemistry is still data poor. But in any case, if I just want to make a quick point here, in terms of what we think the isotope ratios look like, this is helium isotopes, argon isotopes, xenon isotopes. The take-home point would be that these guys are low in ocean island basalts, and they are high in mid-ocean ridge basalts. And how you generate this is what I hope to talk about in the next 15 minutes or so. Patrick?
I just have a sort of silly question, I guess. What happens if the ocean island basalts really do look like atmosphere and you're not introducing any atmosphere? What would be the implications of that?
So one implication could be that the source looks exactly like air, and or that you have heavily recycled atmospheric gases into the sources of mantle plumes. But based on the neon measurements now, we are fairly confident that at least for neon isotopes, that's not the case, that neon isotopes are very different in the ocean islands and the atmosphere. And we think that a lot of the reasons why some of the ratios are low is actually related to this much shallower level contamination process and not associated with deep recycling, although I think that deep recycling of argon and xenon definitely happens. Okay, but the take-home point is low radiogenic to primordial ratios in ocean islands, high ratios in mid-ocean ridge basalts. And the way we do these measurements, just in case you sort of don't know, is we take a lot of glass sample on the order of maybe 5-6 grams, and we stick it in these chambers here with a flexible stainless steel hose, and then we just crush it with the hydraulic ram. And this is in vacuum, so the crushing releases the bubbles, and we trap the bubbles in the high vacuum chamber, clean up the gases like carbon, oxygen, nitrogen, and measure the composition of the noble gases. So in some ways, this sort of is similar to a multi-anvil or a piston anvil device, except the pressures are much, much lower. Now, I'm going to present a few class of models that have been traditionally used to interpret these differences in the isotope ratios. And one of the first models is a steady-state upper mantle. This was proposed back in the early 1990s, and I think Louise Kellogg really laid out the mathematical foundation for this model. And the idea is very simple and it's really elegant, which is to say that the upper mantle is highly depleted. It has been very heavily processed by melting at mid-ocean ridges, such that there shouldn't really be any of these primordial gases left behind. There shouldn't be any helium-3 or neon-22 in this upper mantle. And the only reason why you have even measurable quantities is because there must be a gas-rich reservoir much deeper in the mantle, and that's slowly moving up and fluxing this reservoir with those helium-3 and neon-22. So the idea is this is a very depleted upper mantle. This is a less depleted or a completely primitive lower mantle that's fluxing these elements into the upper mantle. And the prediction from this model is that the depleted mantle and this undepleted mantle will have the same ratios of helium to neon-22, same ratios of helium-3 to argon-36, because these isotopes are not produced in the Earth's mantle. They're primordial. The implication also is that the upper mantle or the depleted mantle and the undepleted mantle will have the same 129 to 130 ratio, because this effectively stopped evolving after 100 million years after the start of the solar system. Once it was clear that there were plates that were getting subducted into the bottom of the mantle, this was slightly modified by Tolsteken and Hoffman, who said, well, instead of having the whole lower mantle being this gas-rich reservoir that's fluxing noble gases into the upper mantle, let's have D double prime at the base of the mantle be this gas-rich reservoir. And this D double prime layer, or gases leaking out of this D double prime layer, is then supplying all of the helium, neon, and xenon into the depleted sources. But this model makes very testable predictions based on what we should observe with respect to the helium-neon ratios and things like that between plume-derived and morph-derived magmas. Here is another very innovative idea that Cinti Lee and colleagues put out, which was, if you go back 4 billion years ago, the mantle was much hotter. A hotter mantle would melt deeper, such as up here. So presently, mantle melting starts at depths of roughly 100 to 60 kilometers underneath ridges. And the idea is here it might actually start melting somewhere around 400 kilometers. And at those pressures, the melt is actually denser than the surrounding material, and so it actually sinks to the bottom of the mantle. And so this melt is sinking to the bottom of the mantle without degassing. And as I told you, that melting will very efficiently transfer the noble gases from this mantle into the melt. This is a very easy way of actually producing a gas-rich reservoir over time. And again, the prediction is that this mantle and this melt will have the same helium-neon ratio and the same helium-argon ratio and so on. And because this process is going on for over 1 billion years or so, you would expect them to have the same 129 xenon to 130 xenon or so on. There's a slight variant of this that Jeff Davis proposed, which was you have reactions between melts and the surrounding peridotite underneath mid-ocean ridges, and that reaction produces peroxenites. The peroxenites are denser, and the peroxenites then sink all the way down to the core mantle boundary at this D double prime layer. So the argument is that only half of the melt is extracted under mid-ocean ridges to produce the ocean crust. The other half reacts with this surrounding mantle to produce these dense peroxenites. And the residence time in this layer is long, on the order of 2 billion years or so. And so because this material above D double prime is turning over much faster, it's losing its primordial gases and evolving to very radiogenic values, whereas long residence time in D double prime makes it less degas, and that's why it has a higher proportion of primordial gases and therefore low ratios of radiogenic to primordial isotopes. So I'm not really going to talk about which one of these models may or may not be right. I'm going to present some observations, and then you can decide yourself as to what you think about the viability of these models. And this, I think, is maybe only 1 or 2 of the data slides that I have. So here are some recent observations that we have. And if you look at these data points, you might think that these are measurements of lots of different rocks. They're not. They're basically measurements of 2 rocks. So the story that I'm going to tell you in the next 15 minutes is based on observations on 2 rocks. So sort of keep that in mind. The atmospheric neon isotope ratio, so 2022, primordial, there is no radiogenic component in here. Helium neon, no radiogenic component here. So the atmosphere lies right there. This is measurements from plume-derived basalt in Iceland. Goes all the way up to about this value of 13. These are measurements from a gas-rich rock from the mid-ocean ridge, from the North Atlantic actually, and it's known as popping rock. The reason why it's called popping rock is because the sample is so rich in gas that when it was brought up to the ship deck, it started exploding. And as some of these explosions are vigorous enough that you'll actually see the rock moving all around the deck of the ship. On a recent cruise that Jonathan was in, he was also fortunate to sample one of these popping rocks, and he didn't realize that these are actually health hazards because you end up shooting shards of glass everywhere. So you want to be working with glasses or something when you're handling them. But the point here is, if you look at these 2 samples, they have very different helium to neon ratios. Okay? And just keep in mind that if you degas something, the ratio will move to the right. This is helium to argon ratio, and this is argon isotope ratio. So this is produced from potassium-40. There's no production of this. There's no production of these 2. The atmospheric composition is down here. This is the composition of the Iceland sample. This is the composition of this mid-ocean ridge basalt sample. And again, they're defining 2 different trends. And I sort of didn't mention why you get these different points based on different step crushes of the rock, is because what you're sampling is a population of bubbles. And so the true mantle composition is somewhere up along these lines, but what happens upon eruption is that you start contaminating these bubbles with atmospheric gases. And different populations of bubbles have different amounts of contamination, and that's why you produce these linear arrays. So these guys are the least air contaminated. These guys lying close to the atmosphere is the most air contaminated. So it's not that there's this range of composition in the mantle for this particular rock. The actual mantle composition is on the end of this line. This is just a shallow level mixing line produced by introducing atmospheric gases into the basalt while they erupt or upon eruption. So the take-home point is that the helium-neon ratio is different. The helium-argon ratio in this plume basalt and this mid-ocean ridge basalt is different. And in this case, you could say, well, if you have a degassing of the mantle source somehow, and I'll talk about this in a few minutes, if you degas the mantle source, you'll move to the right. But in this particular space, degassing also moves you to the right. So that's kind of flipped. Here you would say this is the more degassed source. Here you would say this is the more degassed source. So you can't really explain this difference through any kind of simple degassing process. Question?
So we were seeing earlier in those portions of the talk that there's a fairly high potassium to thorium and uranium ratio there. Can that explain the higher radiogenic argon but less radiogenic neon differences?
So there is no radiogenic neon in this particular diagram. I actually think, yes, part of this difference, so there's also this isotope ratio difference. This is much higher in its argon 40 to 36 ratio than this. And I think this is a reflection of radiogenic ingrowth of argon 40. The reason why I think that this source has a relatively higher proportion of argon 40 is because it is more degassed and it has lost more of the argon 36. So this is low. You produce this from argon 40, you drive up the ratio. Okay. The other point is that you cannot relate this source and this source through recycling of atmospheric gases. So let's assume the whole mantle looks like this, all the way down to the core mantle boundary, and you're introducing plates that are carrying atmospheric gases. So when you mix those two sources, you'll be forced to lie upon this line, because mixing in this space is linear. You're normalizing to the same isotope. So if you start here and you start subducting air, you move down here, there is just simply no way to move in that direction. So this is telling you that there are two different sources, two different elemental ratios that you cannot relate through any kind of simple degassing process.
It assumes that the sources themselves are homogeneous.
That's absolutely, and that's why I said just remember the fact that I'm talking about two samples.
This is sort of a nerdy, rare gas question, but the large error on 4036 for the popping rock, that's counterintuitive.
So the reason why is that this particular steps had very low gas concentrations.
But if that's true, that they got this high 4036 ratio, then they must have had exceedingly small 36, but the error looks small.
Low 36 in these samples?
Yeah.
So
why is the uncertainty large for 40 and then not on the corresponding?
Up here?
No, on the x-axis. You're normalizing both to 36. If you've got a giant uncertainty of 36, why don't you see it on the x-axis?
I think partly, let's see. Sorry. That's a good point. So if you notice, in this particular space, there is no uncertainty in the x direction. And the answer there is no uncertainty in the x direction is because the authors did not report any uncertainty on the helium-argon concentration. So these guys do have uncertainties on the x direction. So there are a couple of powerful statements you can make. You can say that plume gases cannot be supplying helium and neon to the mid-ocean ridge basalt source because they have different helium to neon ratios. You cannot relate the argon isotope composition between the mid-ocean ridges and the plume basalts through simply recycling atmospheric gases. I'm not going to go into this, but there is another set of samples that we have now measured from northern Laos, which does very much look like this Iceland measurement. If you're interested, I can show you that data later on.
I was curious how large would the uncertainty be if you were to plot it on the helium to argon?
Fairly small. So, for example, we think that the uncertainty are on the order of 1 to maybe 2%. here this sort of made a blanket statement like the uncertainties are less than 5%. And we know that the gas concentrations in these different steps varied by more than a factor of 10. So some of them will have much better uncertainties than 5%, and some of them actually might be worse than 5%. Ed. But it's not going to change this position of the line.
I'm sorry if you already said this. If I take one of those black symbols and I'm in my plume, going on my merry way, I don't make it to the surface, and I stay in mantle circulation, and I do whatever for 500 million years, and then I find myself at the mid-ocean ridge.
Mm-hmm.
What will I look like in that plot? I will stay there.
Because remember, as I said, mantle processing through any kind of like tectonic processes like now where you produce plates, you degas them, you put them back, you're not going to change the mantle helium-neon ratio. And there is no real way of changing this isotope ratio. So it's very difficult to change these ratios in the mantle today.
This is pretty profound because geodynamically, now, sidebar, I'm out of my lead. The prediction is, you have these plumes that are an order of magnitude larger than the plausible conduits that get this stuff to the surface. They're, hundreds kilometer type plumes that carry this stuff.
Mm-hmm.
If we buy into that. So a lot of this stuff works its way around. How do you keep that stuff from being seen at mid-ocean ridges just from flow that it'll eventually go through the feeding zone of mantle rock into a mid-ocean ridge? Is it just that we're not sampling the mid-ocean ridges enough to find these here and there that aren't necessarily plumes, but you know what I'm asking?
Yes, I know what I'm asking, and I'm...
Next slide.
I have this data slide. Helium-neon ratio, lead isotope ratio. In morbs. So I don't think anybody has made this observation before, but lead isotope ratio is correlating with the helium-neon ratio. That's telling you something very interesting. And it's basically saying that, comes back to reference frame, that the true morbs actually might not have this ratio. They might be much further out. And so what you're really seeing is a mixture of the two. This has got a lot less of the morb component, and this has got a lot less of the plume component.
I mean, it could very well be that volumetrically the stuff that gives you
Yeah.
the black dot is so small, but we get really lucky because of the partial melting in the very middle of a plume that you get to see it come out.
Sure.
And when it mixes in, by the time we get the morb, it's so trace that forget it.
But I think we definitely see the signal of this plume gas in the morb source. But we think that addition has to happen very recently. It's not a long-term process, meaning you didn't add this plume gas to the morb source 1 billion years ago and just sat around.
Yeah.
Because we're seeing this mixing relationship in present-day morbs. So it's probably like flowing in through the asthenosphere. Rick and then...
There's this lingering memory, too, that back when I was a student, the morph source was a perfectly homogeneous, one composition depleted mantle. And what we know now is that it pretty much has every range of rare earth patterns you can imagine. It's got a wide range in isotopic composition. So the morph source is quite an heterogeneous mixture. I think that's what the lead helium is showing.
That's right.
Yeah, so basically, follow-up question. How confident are we that the source of the plumes and the different volumetric makeup of these different lithologies than the source of the norms?
So we are very...
They must be correct.
So remember, I didn't actually tell you what proportion of the mantle this is representing versus this is representing. I'm just telling you that their sources are different. That when you average them, they look different. So I'm going to resist from actually giving you numbers, because I think that's where the uncertainties come in. Jackie.
Can you show this line as directions of degassing and kinetic fractionation? The degassing is solubility control.
Mm-hmm.
It goes that way. The kinetic fractionation, what is the...
So that would be diffusion controlled.
That's temperature.
Yeah.
Can you clarify that?
So helium would be, for example, helium would be diffusing faster than neon. So that would basically lead to, so for example, if you're here and you lose helium because helium is diffusing out fast, then the helium-neon ratio drops. So, and likewise here, if you lose helium, the helium-neon or helium-argon ratio drops as you move that way because it's diffusing out faster. So I'm going to simplify this because, as we know, actually the mantle has just got two flavors. So this is the red and the blue of seismologists. And if you look at the helium-neon ratio, so this is plumes, this is morbs, nice blanket statement. And the question for you guys is, where do you think the most helium to neon-rich objects in our solar system would lie? So where do you think on this plot sun would lie? Make a guess. Sorry? No. Yeah, like up here? This is a Caltech plot. So that's where the sun lies. Okay. It's lower than both plumes and morbs. Primitive meteorites, carbonaceous chondrites, where would those lie? Relative to the sun? Down there. Okay. No, this actually accounts for the fact that there is some amount of helium-3 in the sun produced from deuterium burning. So you've taken that into effect. But you look at this and you go, and you can, look at Jupiter and you can look at other primitive meteorites, and nothing that we know of has as high a helium-neon ratio as we see either in these mantle plumes or in the mid-ocean ridge basalts. So you cannot explain this through some kind of addition of chondritic meteorites. And likewise, it's very different to explain these two differences through source, through late veneer, or through late accreting material. This must be related to some sort of a process. So this particular ratio in mantle plumes turns out is a factor of 2 higher than what's in the sun, which is interesting because the helium to neon solubility ratio is roughly a factor of 2. So one possible explanation for this was if the Earth was growing very early on when there was still a solar nebula present and you had a magma ocean, you would dissolve nebular gases into the magma ocean, and that would bump up your helium to neon ratio by about a factor of 2. Okay? So that could explain the high helium-neon ratio. But also notice that for the mantle plumes, you're getting to values that are at least 13, and the pure solar wind composition, or the sun, is up here at about 13.8. So it is very conceivable that the deep mantle actually has the exact same neon isotopic composition as the sun. So it has the same neon isotopic composition as the sun and the same helium to neon ratio you would predict by dissolving that gas into the early magma ocean. So that could be one possible explanation for this. But then what about generating this very high helium-neon ratio? That's still a challenge. And again, one possible explanation, and this was proposed in the early 90s by Honda and has largely been ignored, was that this is telling us about the degassing of a magma ocean. So if you degas a magma ocean, then you can drive up this helium-neon ratio very high. You still have the requirement that you can't really degas this particular source too much because your starting values are down here. But you can degas this source quite a bit to move from this value up to there. So this difference could possibly be explained by magma ocean degassing of the morb source. This is not seeing that magma ocean degassing. Colin, you had a question.
Yeah, what explains the difference in the helium-neon ratio between chondrites?
So in general, chondrites are depleted in gases. And the order of depletion is helium is more depleted than neon, and neon is more depleted than argon, and argon is more depleted than xenon. Yeah.
Well, that's a massive fact.
Yeah. So I'm officially out of time. But this is maybe what I wanted you to take away that it's quite possible that in this helium-neon system we might be seeing the evidence of a magma ocean degassing. And that's probably the best explanation for why this ratio is so high. Matt and then Bruce. Yeah, I'm not going to answer that right now. I think it's too complicated for the rest of the people because I haven't even talked about xenon. Yeah. Bruce?
You showed us earlier the fractionation of the helium and neon were quite similar. So I guess I was just wondering a little bit what you had in mind for the gassing process. Degassing from a liquid different.
So as I said, you can, if you have closed system degassing, you can increase that ratio by about a factor of 2. This is close to a factor of 3 or factor of 4. And that's a little bit harder to do with closed system degassing. So it requires probably an open system degassing, meaning some kind of a Rayleigh fractionation process. Now you say, well, you have an atmosphere and you have an open system degassing. What does it mean? Probably means that you are losing gases during this process, that the atmosphere was actually being lost while the magma ocean was degassing.
It doesn't have to be the magma ocean of the Earth. It can be the magma ocean
Of
of
it.
bodies before the
That's
So it can happen early on, actually. It can happen at 3 billion years. It doesn't have to happen at 30.
that's right. But you're seeing that record preserved. Rick?
Am I correct that you can lose helium from the current Earth atmosphere, which
Yeah.
includes neon?
That's right.
So you would have to lose it at a point where you can lose neon, either in a small object or in a really hot Earth. Because if you're
No, that's right. You have to lose neon. That's right.
Missing neon should be in the atmosphere.
That's right. That's right. And part of this is going to be what I'll touch upon in the next lecture as well. You can see that if you simply outgas the mantle, you don't get the atmospheric neon composition. So this is either some sort of a fractionation process that drove you down, or it's telling you that the atmosphere is not derived from outgassing of the mantle, or the noble gases that we see in the atmosphere is not derived from outgassing of the mantle. And so I'll touch upon that in the next lecture. I can keep going if